Isn't just about what is possible. It also laid out what's fundamentally impossible. Today, we're plunging into this really mind-bending area of theoretical physics. It seems the search for the ultimate theory of gravity is telling us that, well, most universes we can even dream of simply can't exist. And it's been stunningly successful, almost unreasonably effective at describing physics at certain energy scales. It's how we got the standard model of particle physics, for instance. But what if? What if a complete theory of quantum gravity imposes these really powerful fundamental constraints? Constraints that make most seemingly okay EFTs totally incompatible with reality.
That's exactly the core idea. That's the Swampland program in a nutshell.
Right. So our mission in this deep dive is to unpack how this radical idea of a swampland even came about. We'll explore the deep limitations quantum gravity seems to place on our universe, and then we'll look at the huge implications these ideas have for, well, everything. From cosmology and the Big Bang to the tiniest particles, maybe even the ultimate fate of the universe. Get ready to rethink what you thought was possible. Okay, so to really get our heads around this, let's start with effective field theory itself. Its success. It sounds a bit weird maybe, but EFT is brilliant at what you called parameterizing our ignorance. It lets us describe things, say, at the scale of an atom without needing to know everything about higher energies, like inside a proton or, the Planck scale where gravity gets quantum.
Exactly. The standard model is the prime example. It works so well, makes such precise predictions, because the effects of whatever unknown physics lies at much higher energies are suppressed. They're tiny at the scales we usually probe. And the standard assumption, building on that success, has always been, well, if your low-energy theory is mathematically consistent, free of paradoxes and infinities, then you should be able to embed it in some deeper, higher-energy UV theory. That was the bedrock idea.
Right. It seems logical.
But the Swampland program just challenges that directly, head on. It says, look, when that UV completion must include a consistent theory of quantum gravity, suddenly the rules change. The requirements for a viable low-energy EFT become incredibly restrictive, dramatically so. It turns out most of these seemingly perfect EFTs, when you try to actually couple them to gravity in a consistent way, they just fall apart. They can't exist in nature.
Wow. So it's like our neat little low-energy theories need a special password, a secret handshake, to be allowed in a quantum gravity universe.
That's a good way to put it, yeah. Quantum gravity is apparently extremely picky.
Okay, that sets the stage. But to really understand why this whole program started, we need to talk about string theory for a minute. There was this dream, right? That string theory would just fall out of the math. That mathematical consistency alone would force it to predict our specific universe. The forces, the particles, everything. Why was that initial idea so compelling?
Oh, it was a beautiful vision. Really elegant. The math of string theory seems so unique, so constrained. It suggested maybe it was the theory of everything, with no dials to turn, just one unique answer. Reality.
But that's not quite how it panned out.
No, that dream was, well, it was kind of shattered, really, in the early 2000s. The big realization was that string theory doesn't seem to predict one single vacuum state for the universe. Instead, it predicts this colossal landscape, possibly 10 to the 500 distinct solutions, maybe more.
10? With 500 zeros after it? That's just mind-boggling.
It really is, and you should think of each of those solutions as a different possible four-dimensional universe, each one potentially having its own set of physical laws, particles, fundamental constants.
How does that happen? Where do all these possibilities come from?
It comes from the complexity of the theory. Things like how extraspatial dimensions might curl up really small. That's Kaluza-Klein compactification. There are countless ways for them to do that. And also how various background fields, these moduli, settle into stable values. Each combination defines a different point in this landscape.
And this sheer number of possibilities, this landscape, created a massive problem for string theory itself, didn't it? The predictivity problem.
Absolutely.
If the theory allows basically anything, or near enough, how can it actually predict anything specific about our universe? I remember it led to some pretty harsh criticisms, like, is this even science if it can't be falsified?
Exactly. If you can explain any observation by just saying, oh, we just happen to live in that corner of the landscape, then prediction becomes very difficult. So it was in that context, around 2005, that Kumran-Vafa introduced these terms to clarify things, landscape and swampland. The string landscape is the set of low-energy EFTs that do seem consistent with string theory, with a proper UV completion in string theory. These are the potentially good theories.
Ones that could be real universes.
Right. And the swampland is everything else, all those other EFTs that might look perfectly fine on their own, mathematically consistent at low energies, but crucially, they are fundamentally incompatible with any consistent theory of quantum gravity. Not just string theory as we know it, but any possible theory. They're mathematical possibilities, sure, but they're not physically realized. They can't be.
So the central idea, the really foundational claim here, is that the swampland is just vastly, vastly bigger than the landscape.
Overwhelmingly so, yes.
Quantum gravity is incredibly picky, carving out this tiny, tiny island, the landscape, from this enormous ocean
Right.
of apparently possible but ultimately inconsistent theories, the swampland.
Precisely. And the Swampland program is the research effort that grew out of that realization. Its goal isn't necessarily to find our specific vacuum in the landscape anymore, but rather to map the boundaries of that island, to establish universal rules or criteria that any theory must satisfy to be on the island, to be in the landscape. These are the Swampland conjectures.
Ah, okay. So how did that help with the predictivity problem?
Well, it gives predictivity a different flavor, a powerful negative predictivity. By defining the properties of theories that are definitely in the swampland, the impossible theories, the program makes concrete, falsifiable claims. If you cook up a new theory, say for inflation or dark energy, and it violates one of these established swampland conjectures,
Then you know it's wrong. You can't describe our world.
exactly, it's ruled out. So it shifts the goal from finding the theory of everything to defining the theory of what is possible by showing what is impossible.
That's a really interesting way to frame it. Okay, so where did these rules, these conjectures actually come from? They aren't just pulled out of thin air, surely.
No, not at all. The idea that most EFTs are in the swampland, it's motivated by some deep physical thinking. It really comes from two main areas. First, thinking about the universal properties of black holes. And second, looking for recurring patterns and structures within string theory constructions themselves. The hope, or the working hypothesis, is that these principles aren't just string theory artifacts, but fundamental features of any quantum gravity theory.
Black holes as theoretical labs. We hear that a lot. But how do they act as consistency checkers here?
Well, think about how black holes behave. Their formation, their evaporation through Hawking radiation, their entropy. All these processes must respect fundamental laws like quantum mechanics preserving information and thermodynamics. Let's take the no global symmetries conjecture. It's a key one.
Yeah.
It comes from the no-hair theorem for black holes. Basically, black holes only remember certain charges associated with long-range gauge forces, things like electric charge. They forget about any other type of conserved quantity, a global charge that isn't tied to a force like that.
So information just gets lost.
Well, if you had an exact global symmetry, a black hole could form carrying that global charge, then evaporates completely via Hawking radiation, which doesn't seem to carry that charge. The charge would just vanish from the universe. That would violate the conservation law. Or the alternative is maybe tiny, stable black hole remnants are left behind, each carrying a bit of the charge. But having an infinite number of possible remnant types leads to its own theoretical problems, like infinite pair production.
I see. So either way, it's problematic.
Exactly. So the conclusion is, in a consistent theory of quantum gravity, there can be no exact continuous global symmetries. Any symmetry has to be gauged or somehow explicitly broken.
Okay, that makes sense. No fundamental properties that can just vanish without a trace or cause paradoxes. What else do black holes tell us?
Another really crucial one is the weak gravity conjecture, the WGC.
The gravity is the weakest force idea.
Yeah, that's the slogan. It's motivated by thinking about extremal black holes. These are black holes with the maximum possible charge for their mass. They have zero temperature, so naively, they can't decay via Hawking radiation. They seem stable.
Which could be a problem.
It could be, especially in theories without supersymmetry. For these black holes to decay, there must exist some particle they can emit. And for a particle to escape a charged black hole, its repulsive electric-like force has to be stronger than its gravitational attraction to the black hole.
Ah, so charge has to beat mass in the right units.
Precisely. The WGC states that for any gauge force, there must exist at least one super-extremal particle, one whose charge-to-mass ratio is greater than the extremal black hole limit. This ensures all black holes can eventually decay. Gravity must be weaker than the gauge force for at least one state. And interestingly, you can even get hints of this from thinking about black hole entropy, the Bekenstein-Hawking entropy.
How does that connect?
Well, black holes have finite entropy related to their area. If you just take a generic low-energy EFT, sometimes it seems like you could form arbitrarily small black holes, maybe an infinite number in a finite space, which would violate entropy bounds. To avoid this paradox, the EFT has to break down at some energy scale. And remarkably, the scale where it needs to break down often matches the scale predicted by the WGC, where these new light, highly charged states should appear.
That's pretty cool. It's like thermodynamics itself is hinting at the WGC. So black holes provide these general, powerful arguments, but string theory is our main example of a quantum gravity framework. How does it give us concrete examples of these ideas?
Right. String theory provides the test cases. The Swampland distance conjecture, or SDC, is a perfect example that came from studying patterns in string theory.
Okay, the SDC, what's the idea there?
It says that if you move an infinite distance in the space of scalar fields that define your universe, like imagine changing the size of an extra dimension continuously, then an infinite tower of new states must become exponentially light. Their mass drops incredibly fast.
An infinite tower.
An infinite tower. We see this all over string theory. Take a simple example. An extra dimension curled into a circle. If you make the circle radius infinitely large, you get an infinite tower of Kaluza-Klein states particles moving in that extra dimension, becoming lighter and lighter.
Okay.
But string theory has dualities. If you shrink the circle radius to 0, which is also an infinite distance in the moduli space, a different tower of states, called winding modes, becomes exponentially light.
So either way, you go to infinity.
Either way, new physics emerges. The original low-energy EFT breaks down. You can't trust it over an infinite range in field space. New light states always appear at the boundaries.
It feels like a fundamental no free lunch principle again. Quantum gravity prevents these idealized infinite limits that you might have in just plain field theory. It forces change, decay, new stuff to emerge.
That's a great way to capture the theme, yes. And these principles are assumed to be universal, the principle of universality. Even though string theory is our best lab, the black hole argument suggests these rules should apply to any consistent quantum gravity theory.
Okay, we've covered no global symmetries, weak gravity, and the distance conjecture. You mentioned a fourth main pillar, the controversial one.
Yes, the de Sitter conjecture, or DS conjecture. This is probably the one causing the most headaches right now.
Why that?
Because it proposes that stable or even long-lived metastable de Sitter vacua are fundamentally inconsistent with quantum gravity.
And de Sitter vacua are universes with a positive cosmological constant, like ours seems to be.
Exactly like ours seems to be. The original version of the conjecture was quite strict, basically saying the potential energy landscape, V for scalar fields, couldn't be too flat where it's positive. Its slope had to be steep enough compared to V itself. There are refined versions now, slightly more technical, allowing for minima that are sufficiently unstable, negative curvature, but the core tension remains. Truly stable, positive energy universes might be forbidden.
But hang on. Our universe is accelerating. We measure a positive cosmological constant, dark energy. If the DS conjecture is right, doesn't that create a massive problem?
It absolutely does. It's a huge potential conflict. It means either our standard cosmological model, CDM, with a constant dark energy is wrong, or the DS conjecture needs serious modification, or maybe string theory itself isn't capturing the full picture of de Sitter space.
So this is where the debate gets really intense.
Very intense. It's pushing theorists to explore alternatives, refine the conjecture, or find clever ways around it within string theory, if possible. And what's really compelling, and maybe gives us confidence we're onto something real, is how interconnected these conjectures seem to be.
They're not just separate rules.
No, they form this intricate web. The WGC is like a quantitative version of no global symmetries for gauge charges. The light states predicted by the SDC often turn out to be the super extremal starts needed for the WGC. And maybe most strikingly, people have found arguments suggesting that the refined DS conjecture might actually be derived from combining the SDC with fundamental thermodynamic bounds, like the Busso entropy bound, when applied to cosmology.
Wow. So they might all be different facets of the same underlying quantum gravity constraints.
That's the hope. It paints a coherent, though definitely challenging, picture.
Okay, this is clearly shaking things up theoretically. Let's talk cosmology. What are the really big implications if these swampland ideas are right?
Oh, they're potentially revolutionary. Let's start with the very early universe, cosmic inflation.
Inflation is our standard story for how the universe got so big and smooth.
It is. Hugely successful paradigm. But The simplest, most elegant models of inflation are in direct tension with the Swampland conjectures.
How so?
Well, standard slow roll inflation needs the inflaton field to roll down an extremely flat potential energy landscape. Very, very flat.
But the DS conjecture says potentials can't be too flat if they're positive.
Exactly, direct conflict. The DS conjecture demands a certain steepness. Also, models called large field inflation, where the inflaton field travels a huge distance, run into trouble with the SDC.
Because the SDC says moving a large distance should trigger new light states.
Right, and those light states could mess up the smooth inflationary process.
So is this the end for inflation?
Not necessarily, but it strongly disfavors the simplest models. It points towards more complex scenarios. Maybe inflation involved multiple fields interacting in clever ways. Or perhaps something like warm inflation, where the inflaton constantly produces radiation as it rolls, which allows it to roll slowly, even on a steeper potential, potentially consistent with the DS conjecture.
Okay, so inflation gets more complicated. What about dark energy, the thing driving acceleration now?
This is where the DS conjecture hits hardest. It essentially forbids a perfectly stable, constant cosmological constant site in the standard ACDM model.
So no vacuum energy as dark energy.
Not a stable one, according to the conjecture. This forces us towards dynamical dark energy models. The leading candidate is quintessence.
Quintessence. That's where dark energy is a field rolling down a potential.
Precisely. It's a scalar field slowly evolving, and its potential energy acts like dark energy. Since the field is rolling, the potential can be steep enough to satisfy the DS conjecture.
And that makes a prediction.
A very clear, testable prediction. The dark energy isn't constant. Its effect should change over cosmic time. Its equation of state parameter, Wi, shouldn't be exactly -1, it should be evolving.
And that's fascinating because, as you know, the big DSI results released in 2024, they showed these hints, right? Tentative, but hints that W might be changing, that dark energy might be weakening.
Exactly. It was incredibly exciting. If those hints solidify with more data, it would be stunning support for quintessence and, indirectly, for the Swampland picture.
And some models connect this rolling field to dark matter too, potentially easing the Hubble tension.
Yes, there are models where this quintessence field interacts with dark matter, sometimes called fading dark matter scenarios, which could potentially alleviate the discrepancy in the expansion rate measurements. It's all very active research. Now, let's combine quintessence with the SDC. If the quintessence field is rolling,
It's moving across field space.
and if it keeps rolling, eventually it will cover a vast distance, likely super Planckian.
And the SDC kicks in.
The SDC dictates that an infinite tower of new states, probably some hidden dark sector states, must become exponentially light.
What would that do?
It would fundamentally change physics as we know it. It would likely trigger a cosmic phase transition, ending the current era of acceleration. It predicts an end to our universe, maybe in a few trillion years.
An actual predicted end.
They predicted end to this phase, yes, which, intriguingly, also offers a potential solution to the coincidence problem.
Why, dark energy and matter are comparable now.
Right. If the accelerating phase has a finite lifetime because of this SDC effect, then it's perhaps less surprising we find ourselves living during the period when dark energy is important. We couldn't exist too early or too late in this specific cosmic chapter.
So the Swampland dictates the beginning, the present, and possibly the end of the universe.
Yeah.
But it also reaches down to particle physics. I heard something about neutrinos being like a canary in the coal mine.
That's a great way to put it. It's quite surprising, but yes. When you take the standard model and sort of compactify it down to 3 dimensions, a theoretical exercise, and then apply certain Swampland conjectures related to the stability of different types of spacetime, a really profound conclusion seems to emerge about neutrinos.
Which is...
Neutrinos must be Dirac particles, not Majorana particles.
Okay, remind me of the difference.
The Dirac particles have distinct antiparticles, like electrons and positrons. Majorana particles are their own antiparticles. It's a fundamental difference. If neutrinos were Majorana, certain Swampland conjectures related to the stability of anti-de Sitter space, ADS, seem to be violated in this 3D setup.
So the Swampland prefers direct neutrinos.
It strongly points that way. And furthermore, it seems to put an upper bound on the mass of the lightest neutrino, suggesting it should be very light, around the milli-electron-volt MAVE scale.
That's a concrete prediction, and it challenges some popular models.
It definitely challenges the standard seesaw mechanism, which naturally explains small neutrino masses, but usually predicts them to be Majorana. So future experiments looking for Majoran in nature, like neutrinoless double beta decay or precisely measuring neutrino masses, are incredibly important tests of these swampland ideas. And it doesn't stop with neutrinos. The WGC puts constraints on axions, these hypothetical particles that are candidates for dark matter, and might have played a role in inflation. The Swampland program might even offer a new angle on the electroweak hierarchy problem, why the Higgs mass is so much lighter than the Planck scale. Perhaps the SDC's Tower of Light states is involved. There's even a more speculative but quite complete scenario called the dark dimension hypothesis.
Dark dimension.
Yeah, guided by swampland ideas, it proposes one extra dimension is actually quite large, micron-sized. It tries to unify dark energy and dark matter, as Kaluza-Klein gravitons from that dimension, and make specific predictions for sterile neutrino masses and the QCD axion mass. Still speculative, but shows how these principles can inspire new model building.
Wow. Okay, so tracing it all back, from black hole physics, string theory patterns, down to the nitty-gritty of neutrinos and maybe even dark matter. The Swampland program is basically asserting that the ultimate laws of quantum gravity are incredibly restrictive. They leave a clear fingerprint on the low-energy physics we can observe.
That's the claim. A very bold claim.
Saying most theoretical universes we could write down are just impossible, not part of the landscape.
Absolutely. And look, these are still conjectures. They're being tested, debated, refined. The DS conjecture, especially regarding our own universe, faces major scrutiny.
It's high-risk, high-reward science.
Definitely. It's pushing the boundaries, forcing us to develop new cosmological models that are swampland consistent, pushing us to understand the deep mathematical structure. The conversation is incredibly lively.
It really feels like a fundamental shift in perspective, doesn't it? Away from that old dream of predicting everything uniquely, towards a perhaps more practical but still profound goal, delineating what is possible by rigorously identifying what is impossible.
Discovering the universe's hidden design rules, you could say.
So, given these potentially profound constraints coming from quantum gravity, what other impossibilities might be out there waiting to be uncovered? And how might things we observe every day, maybe even subtly, be hinting at them right now?
That's the big question, isn't it?
Something for all of us to think about. Keep exploring, because figuring out the rules of the swampland might just be the key to truly understanding our cosmic home.